Hi, my name is Michael Pendazis, and this is online lesson number 2 for Linear Algebra Math 231. We are currently on Chapter 3 of the book, of the textbook for the course, Elementary Linear Algebra by Howard Anton, 11th edition. Okay. Last lesson, we went over 3.1 and 3.2. So in this lesson, we still have to finish 3.2, cover 3.3 on orthogonality, and if there's time, we can talk about 3.4, the geometry of linear systems. Okay? If you watched my first video, I've had the title wrong. I wrote problem and statistics here. It's now correct. Okay? And so this is linear algebra. Okay, so let's go. Okay. So continuing 3.2, continuing 3.2, we have definition 3 of that section. This is 3.2 continued. Okay, and so definition 3 of 3.2 is if U and V are non-zero vectors in 2 space or 3 space, so they're both in 2 space or 3 space, and if theta is the angle between U and V, then a dot product of U and V denoted by U dot V is defined as U dot V is equal to norm of U times norm of V, that's just regular product there, that dot, times norm of V cosine theta. That's equation 12 in 3.2. Okay? If U equals 0 or V equals 0, then U dot V is equal to 0. Okay, and so this is definition 3. This is the definition of the dot product of non-zero vectors U and V in R2 or R3. Okay? U dot V is equal to norm of U times norm of V times cosine of the angle between them. Okay? And as a note, as an important note to this definition, to equation 12, solving for cosine theta in equation 12, we get that the cosine of theta is equal to U dot V over the norm of U times norm of V. Okay, so if we solve for cosine theta here, and we divide both sides by norm of U times norm of V, then cosine theta is U dot V over the norm of U times norm of V. So theta is acute if U dot V is positive, and theta is obtuse if U dot V is negative. And theta is pi over 2 radians, which is 90 degrees. This is 90 degrees. But it's also pi over 2 radians, so it depends on the unit of measurement of your angle we're talking about, right? So usually in calculus and for higher level math, you want to talk about the measure of an angle in radians. And so here we're saying theta is pi over 2 radians, but if you convert that pi over 2 radians to degrees, it's 9 degrees. Just like you convert feet and inches, one to the other, you can convert radians to between radians and degrees. Just 2 different measurements for an angle, okay? Unit of measurement for an angle. So theta is pi over 2, which is 90 degrees, and that's when that's if U dot V is equal to 0. Okay, so by knowing the sign of U dot V, you could know what type of angle you have. So if U dot V is positive, then the theta, the angle between U and V, is between 0 and 90 degrees, strictly between 0 and 90 degrees. If U dot V is negative, less than 0, then your angle theta is obtuse, so you have an obtuse angle. And if U dot V is 0, then the angle between them is a 90 degree angle. So, right, acute angle would mean, right, your U here and your V here, and the angle between them, theta, is acute. Here, the angle, the vector u here and the vector v there, the angle between them here, theta, right? That would be an obtuse angle. And if you have a vector u here and a vector v here, if u dot v is 0, the angle between them is a right angle, 90 degrees, pi over 2 radians. Okay, and so why, right? Okay, so if you look at the values of cosine theta, which I think the easiest way to visualize the values of cosine theta is by remembering how the graph of cosine theta looks. And so here, if you have theta and you have the value of cosine theta, right, their values range from -1 to 1. And so if you look at the value of cosine theta between 0 to pi, then cosine theta, this is the graph of y equals cosine theta. Okay, so the graph of y equals cosine theta looks like that from 0 to pi. Okay, and so the angle between two vectors, we're talking about the angle between them being at least 0 radians and at most pi radians, or at least 0 degrees and at most 180 degrees. And that's because however you position your angles, your vectors, let's say you have your vectors like this, then the theta is going to be the closest way to get from one vector to the other. And so the furthest away these vectors could be is, even if you looked at an angle that you might think of as more than 180 degrees, just go in the direction where it's not more than 180 degrees. So for instance, this way, if you went counterclockwise, you would get more than 180 degrees. Just go the shorter way, and you would still get an angle that's less than between 0 and 180 degrees, or pi. So we only care about cosine theta from 0 to pi radians. Okay? Now, if u dot v is positive, right, this denominator is the product of the norm of two vectors. That's always positive. Okay? We're dealing with two non-zero vectors here, right? If u and v are non-zero, so that means their norms are non-zero, right? We had the fact that the norm of a vector is equal to 0 if and only if the vector was 0, right? These are equivalent, saying the norm vector is 0 and the vector is 0. And so saying that they're non-zero vectors mean that their norms are non-zero. So you can divide by their product because this is a product of non-zero numbers, and so a product of non-zero numbers is non-zero. So you're allowed to divide by the product of the norm of u times the norm of v if you have two non-zero vectors u and v. Their norms are also non-zero. But then, importantly though, the norm of u and v, they're both not 0, and they both have to be greater or equal to 0. These are both positive numbers. And so u dot, the denominator is always positive. And so if the u dot v is positive, that means you take a positive and you divide by positive. You're saying cosine theta is positive. And if you look at the graph of cosine theta, it's only positive between 0 and pi over 2. That's an acute angle. And so the fact that if u dot v is positive, that means you have a fraction with the numerator and denominator positive. You're saying the value of cosine theta is a positive number. And that only happens when, right, its graph is above the x-axis. And that only happens between 0 and pi over 2 radians. That only happens if you're dealing with an acute angle. If u dot v is negative, that means the numerator is negative and the denominator is positive. That means the fraction is negative. And so then cosine theta is negative, and that means the graph is below the value of the graph is below the x-axis. That means the angle between u and v is between pi over 2 and pi. And that means your angle is obtuse. Okay? So if u and v are two vectors whose dot product is negative, that means the value of cosine theta is negative, as the negative over positive. And so the sign of u dot v completely determines the sign of cosine theta, because you're always dividing by positive. And so that means the value is negative and it's not obtuse angle. And then if u dot v is 0, that means you're taking the number 0 and you're dividing by a non-zero positive number. So you get 0. So if u dot v is 0, cosine theta is 0, and that only happens when theta is exactly pi over 2, or 90 degrees. And so you can see from this formula how, when solving for cosine theta, knowing whether u dot v is positive, negative, or 0, you can determine whether the angle between the two vectors is acute, obtuse, or 90 degrees, or pi over 2 radians. Okay, and so it's all from equation 12. The definition of the dot product of two non-zero vectors. Now, if either vector is 0, the dot product is 0. Okay, and and also the angle between them is 0. Right? If either vector is 0, then you can make the direction of that 0 vector the same as the other vector, and the angle between them is 0 degrees. And so then theta is 0. Okay? If either of them is 0. Okay, so we cover all possibilities here. I mean, if you said the angle between them was 180 degrees or pi radians, you would still get 0 there, but that'd be kind of a silly way to do it. It's better just think of it as 0 degrees, not 180 degrees. Okay, so that's how we exhaust all possibilities. Okay, so example 5. If we have the x-axis here, the y-axis here, x, y, and z-axis here, then if you have the u vector here, which goes in the z direction, positive z direction, and you have a vector v here that goes off in this other direction. Now let's say the vector v is the vector 0, 2, 2. And let's say the vector u is 0, 0, 1. Okay, so u and v are those vectors. Now, the angle theta here is between vectors u and v, and that angle theta is 45 degrees. Okay? And so, if you want to compute the dot, so the goal here is going to be to compute the dot product of u dot v. And this is figure 3.2.5 in the book. Okay? So the goal is find u dot v. Okay? So we're going to find u dot v. So by definition, u dot v is equal to the norm of u times the norm of v times cosine theta. Okay? And so what do we need to find? We need to find the norm of u, the norm of v, and cosine theta. Then we just multiply those three and we get u dot v. Okay? So we need to find norm u, norm v, and cosine theta. So let's find the norm of u. So remember, u is the vector 0, 0, 0, 1, and v is equal to 0, 2, 2, and theta, the angle between them, is 45 degrees. Okay, so this is the information we need to get all that. So the norm of u is the square root of the sum of the squares of the components of vector u. And so this is equal to 1. The norm of v is equal to the square root of the sum of the squares of v. That's the square root of 8. That's 2 root 2. Okay, so that's the norm of u and norm of v. Theta is 45 degrees, so what's cosine of theta? That's cosine of 45 degrees. You could write that as pi over 4 radians. Cosine of pi over 4 radians, but cosine of 45 degrees is root 2 over 2. Okay? Okay, so we found norm of u, norm of v, and cosine theta. Okay, so you know this from trigonometry and pre-calculus. Okay. So u dot v is equal to the norm of u times the norm of v times cosine of 45 degrees. Because that 45 degrees is in between them. And so this is equal to 1 times 2 root 2 times root 2 over 2. And that is equal to 2. Root 2 times root 2 is 2. And then the 2's cancel. And root 2 times root 2 is 2. So u dot v is equal to 2. And that's the end of that question. We found, so the goal was find u dot v. U dot v is equal to 2. And so we answered our question. Okay, let's keep going. Okay. All right, let's keep going. So another formula. So if the vectors u and v are in 3 space, then u dot v is equal to u1 v1 plus u2 v2 plus u3 v3. This is equation 15. Okay, and so I should point out that this dot product I'm using is an inner product. It's called an inner product, and we're going to talk about later how an inner product function is actually more general than just this one. And so this is one example of a dot product of two vectors. Okay, so it doesn't have to equal this, but right now we're talking about one particular dot product, one particular inner product, which is that. Okay. So the dot product of two vectors in R3, one way to define an inner product between two vectors is like that. Okay? Okay. If u and v are in two space, then u dot v is equal to u1 v1 plus u2 v2. Right? So I left out the thing that says, what the components of u are. U is equal to u1 comma u2, and v is equal to v1 comma v2. Right? And so u1 is the first component of u, v1 is the first component of v, u2 is the second component of u, v2 is the second component of v, right? Okay, so when you see those symbols, you know that that's what that means, and we don't have to write out all that. Okay, so that's equation 15 and 16, definition 4. If u, and now I'm going to write it, if u is u1, comma u2, comma dot dot dot, comma un, and v is because it's a definition, so I just want to make sure that it's clear that you know what I'm saying about a definition before you use it for everything. If u is that and v is that, are vectors in Rn, then u dot v is defined as u dot v is equal to u1 v1 plus u2 v2 plus dot 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 plus un vn. Okay, so again though, a dot product is one of the several forms something called an inner product function can take. So this is one form of an inner product. Okay, and so right now we're looking at one particular example of an inner product or a dot product. Okay. And so that example is that you multiply the corresponding components of two vectors and you add up those products. So the first component of u times the first component of v plus the second component of u times the second component of v plus dot 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 plus the nth component of u times the nth component of v. And so that's equation 17 in 3.2. Okay, so that's the definition for u dot v. Okay, so example 6, we're going to compute this dot product. Find, using this definition, dot product. Find u dot v, where u is -1, 3, 5, 7, and v is equal to -3, -4, 1, 0. Okay, so that's u, that's v, and so u dot v is just the first component of u times the first component of v plus the second component of u times the second component of v plus the third component of u times the third component of v plus the fourth component of u times the fourth component of v. What's that? That's equal to 3 plus -12 plus 5 plus 0, and that's -4. Okay, so u dot v is -4 in example 6. 3.2. Okay. So from that definition of dot product, you can say that v dotted with itself is equal to v1 squared plus v2 squared plus dot 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 plus vn squared, and that's equation 18. Okay, and so also we can say that the norm of v is equal to the square root of v dot v, and that's equation 19. So these are two new equations that you can now use when you're doing around. Okay, and so what are the reason why? So the reason for these two equations, why these two are true, All right, we defined u dot v is equal to u1 v1 plus u2 v2 plus dot 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 plus un vn. So v dotted with itself, you're just going to take the first component of this vector times the first component with that vector, with the same vector, plus the second component of that vector v times the second component of the same vector plus dot 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 plus the nth component of that vector times the nth component of the same vector. That's v1 squared plus v2 squared plus dot 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 plus vn squared. And so now we showed that v dotted with itself is the sum of the squares of its components. Okay? Now, so that shows that v dot v is equal to the sum of the squares, and we proved equation 18. Okay? Now, if you take the norm of v, by definition, that's the square root of v1 squared plus v2 squared plus dot 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 plus vn squared. By definition. But the sum of the squares here I just said is v dot v from the last thing here, right? This thing I circled v dot v is equal to that thing I circled the sum of the squares, so the components of v. So now within the square root is the exact same thing, this. And so instead of writing this, I can write v dot v. So this is equal to the square root of v dot v. And now what I show is that the norm of v is equal to the square root of v dot v. And so now we proved 19. So now we have these two equations and the proof for those two equations. Proofs for those two equations. Okay, and so that's how our mathematician works. We make a statement and then we justify it with a proof. Okay, so what we did here was we made two statements and we justified those two statements and we showed the reason for why they're true. Okay, so next is theorem 3.2.2. And this theorem says if u, v, w are vectors in Rn, I left out R vectors. Okay, so we understand that they're vectors. If u, v, and w are vectors in Rn, and if k is a scalar, okay, then we can make the following statements. A, that u dot v is equal to v dot u. This is called the symmetry property. B, u dot v plus w is equal to u dot v plus u dot w. C, k times u dot v is equal to ku dotted with v. D, v dot v is greater or equal to 0, and v dot v is equal to 0 if and only if v is equal to 0. So the and here is referring to that if and only if statement. This is the biconditional again, and that this is the notation for if and only if. Right? So that means that this statement, v dot v equals 0, has the same truth value as v equals 0. As the statement v equals 0. Okay? And so D is saying that v dot v is greater or equal to 0, and v dot v equals 0 has the same truth value as v equals 0. Okay, and so that's theorem 3.2.2. Okay, these are for three vectors u, v, w in n space, and k is any scalar. Okay. So in C, we're taking k times the dot product of u and v, k times u dot v. And so what C is saying is that k times u dot v is equal to k times u, ku dotted with v. Okay. Here we're taking the dot product first, then multiplying by k. Here we're multiplying the first vector u by k and then taking the dot product. So we're changing the order. But C is saying that you can change the order of these two operations and you still get the same result. Okay. Theorem 3.2.3. If u, v, w, if the vectors u, v, w are vectors in Rn, and k is a scalar. Okay, so by writing k scalar, I'm saying k is a scalar, and k is a scalar. Then A, 0 dot v is equal to v dot 0 is equal to 0. B, u plus v u dot v minus w is equal to u dot v minus u dot w, and d u dot kv. Okay, so in theorem 3.2.3, if u, v, and w are, again, vectors in n space, and k is any scalar, so we have the same u, v's, and w's and scalar k, then we can make 5 more statements about this situation. 0 dot v is equal to v dot 0 equals 0. So if you dot product a vector with 0 in either order, it equals 0. U plus v dot w is equal to u dot w plus v dot w. U dot v minus w is u dot v minus u dot w. Okay. E is like what we saw in C in the last theorem. K times u dot v is equal to u dotted with kv. So now we're just changing the order again, right? Instead of taking the dot product and multiplying by k, we're going to just change the order in a different way, where now we're going to multiply k by v first, and then take the dot product with u, for u dot kv. Okay? And so, so those are 2 more theorems, but 9 more equations, 9 more statements that you can now use. Okay? And so the more equations you have, the more things you know are true, the easier life can get. It's easier to deduce something if you know more than if you know less. Okay, so example 8. So example 8, u minus 2v Okay, so now we're going to take u minus 2v dotted with 3u plus 4v, and so now we're going to take u dotted with 3u plus u dotted with 4v minus 2v dotted with 3u minus 2v dotted with 4v. And so you see how I did this. So I did u dotted with 3u, u dotted with 4v, and negative 2v dotted with 3u, and negative 2v dotted with 4v. I just moved the negative part. Okay. So this is the same as 3 times u dot u. This is plus 4 times u dot v. This is minus 6. 2 times 3 is 6. 6 times v dot u. This is minus 2 times 4, which is 8. 8 times v dot v. And so what I did was I used all the, from the last board, the 2 theorems, those 9 equations, in order to move things around, okay? So I used the distributive properties from the last board to write this as a sum of these 4 terms. And then we know we can change the order of scalar multiplication, right? Remember that k times u dot v is equal to, I could say it's equal to u times dotted with the dot kv. And so in this here, we do that here. U dotted with 3u, that's the same as, instead of u dot v here, it could be u dotted with itself. So here, the way we're using it is 3 times u dotted with u instead of v. K is 3, v is u. 3 times u dot v is going to be u dotted with 3u. And so saying that the u dotted with 3u is 3 times u dot u is using this statement that k times u dot v is equal to u dotted with kv. And here k is 3 and v is u. And then plugging in k is 3 and v is u in that statement, we get that this thing is that. And so you can substitute this with it's that because they're the same. And you could do a similar thing for the rest of it. So now we get this statement here. U dotted with u is the norm of u squared. Okay, so this is 3 times the norm of u squared plus, now we also have that, also remember that we have that u dot v is equal to v dotted with u. And so if you switch the order of the 2 things you're dot producting, it's the same. So u dot v equals v dot u. And so the u dot v and the v dot u here are the same. So this is plus 4 times u dot v minus 6 times u dot v. I'm going to replace the v dot u here with u dot v. This is minus 8 norm of v squared. A vector dotted with itself is its norm squared. And so this is 3 times the norm of u squared. 4 times u dot v minus 6 times u dot v is minus 2 times u dot v minus 8 times the norm of v squared. That's our final answer. So this is the dot product of u minus 2v dotted with 3u plus 4v is equal to 3 times the norm of u squared minus 2 times u dot v minus 8 times the norm of v squared. Okay, and so that's example 8. Okay, so from before, we knew that cosine of theta is equal to u dotted with v over the norm of u times the norm of v. Okay, so we got that from the definition of the dot product. We solved for cosine theta and got cosine theta equals u dot v over the norm of u times norm of v. Now that implies then that theta is equal to cosine inverse of u dot v over the norm of u times norm of v. Okay, and so you just take the cosine inverse of both sides. So cosine inverse of cosine theta is theta, and then cosine inverse on the right side. So theta is equal to cosine inverse of u dot v over the norm of u times norm of v. Okay, and so what this tells you then, what that implies then, well, you're taking the cosine inverse of something, right? And the cosine inverse is a map that takes the value of the function cosine and maps it to the angle that gives you that. So what I mean is, right, this is how inverse functions work again. If you have an angle theta, right, cosine theta will map it to cosine theta, right? That's the cosine function. Right? The cosine function will take an angle and map it to cosine theta. The cosine inverse function will take that value of cosine theta and it will map it back. First, it's going in this direction. Cosine theta is going from theta to cosine theta. Cosine inverse map will take the value of the cosine function and map it back to the angle theta that gave that value to. So as an example of that, if you had the angle, let's say pi over 6 radians, that's your theta. The cosine map would take that number of radians, pi over 6 radians, so that's 30 degrees, and it would tell you root 3 over 2. So cosine of pi over 6 is, or cosine of pi over 6 radians or cosine of 30 degrees is root 3 over 2. Now the cosine inverse graph would take the value root 3 over 2. If you input root 3 over 2, the cosine inverse graph, what that will do is it'll take the value of cosine and it'll tell you the angle, it'll spit out the angle that gives you that value from the cosine graph. So cosine will map pi over 6 to root 3 over 2. Cosine inverse will take root 3 over 2 and map it to pi over 6. Okay, so what does that mean? So theta is cosine inverse of something. That thing, u dot v over norm of v times norm of v. Well, what this is an input for cosine inverse, right? This is something you input into the cosine inverse graph. That input is a value of cosine. We know that cosine of theta is between -1 and 1. The value of cosine theta is between -1 and 1 inclusive. That means that the value of cosine theta, this number here, has between -1 and 1 inclusive. That means the thing that you put into cosine inverse has to be between -1 and 1 inclusive. So that thing that's in the cosine inverse parentheses, we can deduce from that u dot v over the norm of u times norm of v is between -1 and 1. So the input for cosine inverse has to be between -1 and 1 inclusive. So -1 is less than or equal to u dot v over norm of v times norm of v is less than or equal to 1. Okay. Okay. And so now we have this fact. Okay. And so from this fact, we're going to get what's called the Cauchy-Schwarz inequality. So we have that. And the next word, I'm going to write down the theorem that says that. theorem 3.2.4, the Cauchy-Schwarz inequality. So theorem 3.2.4, the Cauchy-Schwarz inequality. If U is equal to U1, U2, dot UN, V is equal to Vn are in n space. So if U and V there are in n space, then U dot V, the absolute value of U dot V is less or equal to the norm of U times norm of V. That's inequality. That's fact number 22. Now it's inequality. In terms of, or this is just another way to write it in terms of components. You can write the same equation, this inequality, as U1 V1 plus U2 V2 plus that plus UN Vn. Right, so that's the dot product, and that's less or equal to is the absolute value of this. Is less or equal to, well, the norm of U is the square root of U1 squared plus dot dot dot, see here, U plus UN squared times the square root of V1 squared plus dot 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 plus Vn squared. And that's inequality 23. Okay, so you can rewrite that inequality in terms of components as that, but it's the same thing. You're just writing more just to say the same thing. Okay, so that's the Cauchy-Schwarz inequality. Okay, and so how do we get that? The proof? Well, in the last board, we showed that -1 is less or equal to U dot V over the norm of U times the norm of V, which is less or equal to 1, right? So we just showed this was true. -1 is less or equal to U dot V over the norm of U times norm of V, less or equal to 1. So now we're going to take the absolute value of that. We're going to take the absolute value, and that implies that the absolute value of U dot V over the norm of U times norm of V. The absolute value of this thing, which is sandwiched between -1 and 1, is less or equal to 1. And therefore, that implies that the absolute value of U dot V is less or equal to, and I'm just going to, thinking of, right, algebra, the absolute value of a fraction is the absolute of the numerator of the absolute value of the denominator. The norm of U and the norm of V are non-zero, because they're non-zero vectors, and it's a product of positive numbers. So the denominator is a positive number, and so its absolute value is the same. So taking the absolute value of something positive is just the exact same thing. So we don't care about the absolute value in the denominator. And I'm just going to move this to the right side with algebra. This is less than or equal to the norm of U times the norm of V. And so now we've deduced that the absolute value U dot V is less or equal to norm of U times norm of V. And that's the Cauchy-Schwarz inequality. So there we just proved equation 22. Yeah, just proved 22. Equation 22. Inequality 22. Okay. So that's theorem 3.2.4, the Cauchy-Schwarz inequality. Okay, so theorem 3.2.5. Okay, so theorem 3.2.5. If U, V, and W are vectors in Rn, so I'm going to write R in Rn, then part A, the norm of U plus V is less or equal to the norm of U plus the norm of v. So this is the triangle inequality for vectors, but you don't need to know the name. And b, the distance between u and v, is less or equal to the distance between u and w plus the distance between w and v. And this is the triangle inequality for distances. Okay, so that's theorem 3.2.5. That for three vectors u, v, and w in n space, then the norm of u plus v is less than the norm of u plus norm of v, and the distance between u and v is less than the distance between u and w plus the distance between w and v. Okay, and so actually a simple way of looking at this is if you think of a triangle where it's made up of vectors, so one side is u, one is v, and the other is u plus v. Okay, so this triangle is going to explain to us part A of theorem 3.2.5. Okay, so we made up this triangle with three vectors. One side is u, one side is v, the hypotenuse is u plus v for this example. Well, so just a rough sketch of this proof is that for a triangle, you know that the length of the hypotenuse is less or equal to the sum of the length of the sides. So, fact about triangles. So a fact about triangles is the length, I'm going to use length as absolute value around it. So the length of the hypotenuse. So my notation is the absolute value around hypotenuse means the length of the hypotenuse is less or equal to the length of one leg plus the length of the other leg of the triangle. Right? Every triangle has one hypotenuse and two legs. So the length of hypotenuse is less equal to the length of one leg plus the length of the other leg. That's a fact about triangles. And so here, the hypotenuse is u plus v. And now the length of a vector, right, is its norm. And so the norm of u plus v is less than or equal to the length of one, which is u, plus the length of the other leg, which is v. And so now this triangle made up of the vectors u, v, and u plus v as hypotenuse means from this fact about triangles, we can say the norm of u plus v is less than the norm of u plus norm of v. And so that proves A. Okay? And now similarly, instead of thinking of a triangle as being made up of vectors, if instead you think of the triangle as just from, you normally would think of it as points, right? Made up of points and line segments connecting those points. And if you think of those points as being labeled u, v, and w, like that, where here's u, here's w, and here's v, right? Well, distance is just, we're using the usual convention for distance. Distance can also be more arbitrary, more general. But we're going to use our normal idea of distance, where distance is the length of the line segment from u to v. And so this length of this line segment from u to v is the distance between u and v. The distance between u and w there is the distance between u and w. V and w. And so now here, so the length of this line segment from u to w is the distance between u and w, and then the distance from v to w is this line segment. This length of this side of the triangle is the distance between v and w. The length of this side is the distance between u and w. The length of the hypotenuse is the distance between u and v. And so by the same fact about triangles, the length of the hypotenuse, which is the distance between u and v, is less or equal to this length of one side, which is distance between u and w, plus the other length, which is distance between v and w. And so now we have part B. Actually, I said w and v, so it doesn't make a difference. I'm going to write w and v that way. So the distance thing is metric, is function is symmetric. You can, doesn't matter the order here. We're going to use the same order. Okay. So now this is less or equal to that. That's part B. And so this proves part B of the theorem. And so now part A and B are both proved. Using the simple fact about triangles that the length of the hypotenuse is less or equal to the sum of the lengths of its two legs. Okay. Okay, so those are figures 3.28 3.2.8 and 3.2.9 respectively. Okay. So theorem 3.2.6, if u and v are vectors in n space, then I'm slowly starting to write less and less. Okay, so if u comma v is in Rn, then the norm of u plus v squared plus the norm of u minus v squared is equal to 2 times and that's fact 24. Okay, so if u and v are vectors in n space, then the norm of u plus v squared plus norm of u minus v squared is equal to 2 times norm of u squared plus norm of v squared. That's theorem 3.2.6. Okay, now theorem 3.2.7. If u and v are vectors in Rn, so if u and v are vectors in n space, with the Euclidean inner product, okay, and so here is where I'm going to just make, by Euclidean inner product, I'm just being more specific about the right way to state the dot product. Euclidean inner product means the thing that we talked about before, that u dot v is equal to u1 v1 plus u2 v2 plus dot 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 plus un vn. The Euclidean inner product is saying that if you take two vectors u and v in n space, right? If you take two vectors in n space, their dot product by the Euclidean inner product is that sum there. Okay? So there's infinitely many inner products you can define. So there's lots of inner products you can define. Specifically, the one we were using is called the Euclidean inner product. Okay, and so not only do we have to say that two vectors are in n space for this theorem, we have to clarify which inner product we're using. We're using the Euclidean inner product. And so then with the Euclidean inner product, the Euclidean inner product of u and v, u dot v, is equal to 1/4 times the norm of u plus v squared minus 1/4 times the norm of u minus v squared. And that's fact 25 in this section. I made a second box by the two boxes share this. So now these two theorems are sharing that border. Okay, so so if u and v are in n space with the Euclidean inner product, then u dot v is equal to that. Okay, but when I specify the inner product as being the Euclidean inner product, right, not only does that matter for what u dot v means, it also matters for what the norm of a vector means. So the norm of a vector is defined by an inner product, and so if you choose a different inner product function, your norms will also be different. Not just the value of the dot product of two vectors, the norm, when you compute the norm, it will also be different. And anything else that depends on the dot product or inner product, if you change the inner product function, then all the definitions that depend on it, the value of those things will also change. Okay, so here, the value of the norms and u dot v, all those things are different if you don't use the Euclidean inner product. And so this equation may not hold for an inner product that's not the Euclidean inner product. Okay, but for this inner product, the Euclidean inner product, this equation holds. Okay. Okay, so that's the end of 3.2. Alright, so that's how a section ends. It gets really confusing or difficult at the very end. Okay, so now that's the end of 3.2. Now we're going to go to 3.3. Okay, 3.3 orthogonality. Okay, so 3.3 is on orthogonality. Theta is equal to cosine inverse of u dot v, the norm of u times norm of v. So we're start off with that. So what we talked about theta is that, okay? This implies that theta is pi over 2 if and only if the u dot v is equal to 0. Okay, so theta is cosine inverse u dot v over norm v times norm v. That implies that theta is pi over 2 if and only if u dot v is equal to 0. So we talked about how, right, the angle between the two vectors is 9 degrees or pi over 2 radians if the dot product is 0 and it works the other way around. So we talked already about that. Now let's talk, now here's the definition. Two non-zero vectors u and v in n space are orthogonal or perpendicular. Perpendicular if u dot v is equal to 0. Okay, so the 0 vector is orthogonal to every vector in n space. Right, we're talking about vectors in n space. Okay, so two non-zero vectors in u and v in n space are orthogonal or perpendicular if their dot product is 0. Right? Saying a dot product is 0 means the angle between them is 90 degrees or pi over 2 radians, and so we could say, instead of orthogonal, we could say they're perpendicular. The 0 vector is orthogonal to every vector in n space. So here's a definition of orthogonality. And this is just an added fact. The 0 vector is orthogonal to every vector in n space, right? And so we say in n space because we're dealing with vectors in n space, and our dot product is only defined between vectors in n space. And so if you were to take the dot product of a 0 vector with a vector that's not in space, it wouldn't be defined, right? Our dot product function only applies to two vectors in the same space, same n space, and so we're only talking about the 0 vector being dot product with a vector in n space, and so we're only going to talk about it being orthogonal to every vector in only n space. Okay? Okay. So example 1. A. If u is equal to -2, 3, 1, 4, and v is equal to 1, 2, 0, -1, then u dot v is equal to -2 times 1 plus 3 times 2 plus 1 times 0 plus 4 times -1. Right, so we're just finding the dot product between the two vectors u and v. We're taking the first components, we're multiplying the corresponding components. So -2 times 1 plus 3 times 2 plus 1 times 0 plus 4 times -1. Right, and so that's equal to -2 plus 6 plus 0 plus -4. And so that's 0. So u dot v is equal to 0. -2 plus -4 is -6 plus 6 is 0. So u dot v is 0. And so here, when u dot v is 0, if and only if, the angle between them is 90 degrees. And here in the definition, two vectors are orthogonal if their dot product is 0. And so therefore, u and v are orthogonal vectors. Therefore, u and v are orthogonal vectors in R4, and this is by the definition above. Okay, so since u dot v is equal to 0, u and v are orthogonal vectors in R4 by the definition above of orthogonal vectors. Okay, so that's part A of example 1. That's part B. So for part B, we're going to let capital S be the set I, J, K. And this is the set, let S be the set of standard unit vectors in R3. Right? And remember those vectors are I equals 1, 0, 0, j equals 0, 1, 0, and k is equal to 0, 0, 1. Those are the standard unit vectors of R3. Those are the unit vectors in the positive direction of the coordinate axes of R3. So here's the x-axis, y-axis, z-axis. This is the unit vector along the x-axis, positive direction. This is the unit vector along the positive direction of the y-axis, and this is the unit vector along the positive direction of the z-axis. Right? And so when you take a unit vector in the positive direction of an axis, there's a 1 in the component of that vector corresponding to the axis you're talking about, and 0 is everywhere else. And so the unit vector along the x-axis, in the positive direction x-axis, has a 1, because you're moving 1 along the direction of the positive x-axis, but then you're not going anywhere in along any other direction of any other axis, so every other component is 0. Okay? So what happens then is, let's talk about the dot products between all the standard unit vectors of R3. And so I dot j is equal to 1, 0, 0, dot 0, 1, 0. And so it's 1 times 0 plus 0 times 1 plus 0 times 0, and then equals 0. J dotted with k is equal to 0, 1, 0, dotted with 0, 0, 1. 0 times 0 is 0, plus 1 times 0, which is 0, plus 0 times 1, which is 0, and that's also equal to 0. And then k times I is equal to 0, 0, 1, dotted with 1, 0, 0. 0 times 1 is 0, plus 0, plus 0, you get 0. Okay? And so now we have the dot products here. And you can switch the order and the dot product stays the same, right? Right. So remember, one fact about dot products was that u dot v equals v dot u. And so for each of these equations, I could have switched the order of the standard unit vectors I was talking about, and it would still be 0. So since I dot j is equal to 0, j dot I is equal to 0. Okay? So by our fact on the board there, j dot I is equal to 0, k dot j is equal to 0, and I dot k is equal to 0. So I can just switch the order of the two vectors I'm dot producting each time, and it's still 0. Because the order doesn't matter. Okay? So that means, though, that I have 3 standard unit vectors, and I can multiply each of them by any of the other 2 in any order. So there's 6 ways to take one of those and first, and then multiply by another one second. Alright, so there's 6 dot products. There's this one, this one, this one, this one, this one, and that one. There's 6 dot products, and they're all 0. So if you take the dot product between any 2 different standard unit vectors in any order, in this example, we get 0. Okay? So thus, each ordered pair of vectors in S is orthogonal. What that means is that here's our set S, and so a shorter way to say it is, if you take your set S here, an ordered pair of vectors in S means just take 2 of those vectors in S, make it an ordered pair, so there's going to be a first one and a second one, and that's going to tell you which one is on the left and which one's on the right, the dot product. So if you take any 2 vectors in that set and you dot product them in either order, you're going to get 0. And so since the dot product between those 2 is 0, they're orthogonal. So every pair of standard unit vectors are orthogonal. Okay, so each pair, so if you choose any 2 standard unit vectors here, they're orthogonal. The angle between them is 90 degrees. Okay. Okay, let's keep going. So basically what I said, if you take any 2 standard unit vectors, they're orthogonal, they're perpendicular, because their dot product is 0. Using the Euclidean unit product. Okay, Okay, so now a new topic, a non-zero vector, little n, called a normal, is orthogonal to the line or plane in question. Okay, so let me draw a picture and illustrate what that means. Okay, so for instance, if you have a line, okay, so if you have a line, a normal is something that's orthogonal to that line. So let's draw a normal. A normal is going to be a vector, I'm going to call little n, that's just perpendicular to the line. And that little n is acting as a normal in that line. And if you have a plane, I'm going to draw a plane here. So let's say you have that plane, but it's not curved. Let me just draw it so it's not curved. So I'm going to draw the lines more straight, just so that you communicate with you what I'm talking about by straight. It's not a paper that's curved, it's paper that's straight. Okay, so there's a plane there, and then a normal would be a vector that's just perpendicular to that plane. And so here's the little n, and so now that's perpendicular. And what does that mean? That it's, how could, what do I mean by it's perpendicular to the plane? Take any vector lying in the plane. Take a vector that's entirely in that plane. So a plane is kind of like a piece of paper that goes out in all directions to infinity in every direction. And so take a vector that's on that piece of paper that's on that plane, then the normal vector is perpendicular to that vector. And so it's not just perpendicular to one particular one you choose, it's perpendicular to any vector that lies in that plane. So no matter what vector you choose on the plane, that n is perpendicular to it. And that's how little n is perpendicular to the entire plane. It's perpendicular to every vector lying in the plane. Okay, and so here we have a normal vector to a line, and here we have a normal vector to a plane. And so these two pictures are illustrating what a normal vector to a line and a plane looks like. Okay. So both a line and plane are represented by the vector equation. N dotted with P naught P is equal to 0. That's equation 1. So in the book there's no parentheses there, but I like putting parentheses places so it's clear what's happening. So I'm N dotting with P naught P. Okay? Where P is either an arbitrary point on the line or the plane. Okay, so I'm going to box this section of it just so that it's separate from the pictures I was drawing up here. Okay, so look inside that box. So both a line and plane are represented by the vector equation n dotted with P naught P equals 0, where P is either an arbitrary point on the line or on the plane, depending on what you're talking about. Okay, so okay, and that P naught is a point on the plane. Let me just add that in. P naught is a point on the line or plane. Okay, so P naught is a point on the line or plane. So now I'm going to just erase these pictures to draw another line or plane. So I'm going to do it to explain what's in the thought. So I want to add something to those pictures to explain this. Okay, so let's say you have, let's go with a plane first, because even though a plane is probably more difficult than a line, I think in the explanation it might be. So here's our plane, and the plane is it's not ending, it's going out in all directions, which these arrows are showing, right? That's the same for the other pictures. So it's just, that's our plane. Okay, and P naught is a point on the line or plane. So here's P naught. P naught is a point on the plane. And so now where P is either an arbitrary, so here's the important thing, where P is either an arbitrary point on a line or plane. So here's a plane. So we're talking about P is an arbitrary point in the plane. So the plane is represented as being the set of all points P that satisfy this equation. Okay, so note the plane here is defined as the set of all points P that satisfy, and by that I mean / make true, the equation n dotted with P naught P is equal to 0. So here's your vector n. And actually, so remember, we don't yet know what the plane is, and we're determining it by this equation. Okay, so this equation is determining our plane. And so if you take any vector, if you're taking a vector n and a point P naught, you're given P naught and you're given n. And all the P's you could plug in there into this dot product to make the equation hold. Those are all the points on the plane. So here's P naught and here's n. So we know P naught, where some point P naught, and we know a vector starting at P naught called n. The initial point is P naught, and then it goes in direction of magnitude defined by your vector n. Now, the plane is defined as being all the points P that satisfy the equation. What does that mean? So if I were to plug in the correct P here, that means that the vector P naught P would be perpendicular to n, because the dot product between n and P naught P would be 0. So if I choose the correct point, a point P that would be in the set that defines that plane, then the vector P naught P would be a vector perpendicular to n, or the dot product of n dot P naught is 0. That's what happened, right? That's equivalent to saying that they're perpendicular, right? So if I choose the right, every point in free space that I could choose, that P naught P would be a vector that's dot product with n is 0, or orthogonal to n. All those points that would make that true, those are all the points on the plane. If I choose the wrong P, a P that's not on the plane, then the vector starting at P naught and going to P would not be perfectly 90 degrees with n. It would not be perpendicular to it, and the dot product would not be 0. And so satisfying an equation doesn't just mean something like 2x equals 4, and the value that solves this equation is 2. And so equations don't just have to be about adding, subtracting, multiplying, and dividing. And so finding all the solutions of equations doesn't just mean solving simple arithmetic problems. Here, solving the equation means finding the point P's such that the vector P naught P dot product with n is 0. And so now the equation you're trying to solve is a dot product equation, is an equation of a dot product of vectors, and you're finding all the points that make a vector P naught P whose dotted with n is equal to 0. And so this is a different type of equation. So this is not solving an arithmetic equation. This is solving a dot product equation. Okay? Okay, and so that's it. So the plane is a set of all points P such that the vector starting at P naught and going to P is perpendicular with the given vector n. Or that this equation is true. From that fact, that note there. Okay? Okay, and so read that to understand this. Okay. That's explaining this. Okay, and so this equation is the point normal form. It's called the point normal form. And so this is the point normal form of an equation of a plane. And by what it's this equation. So n dot of P naught P equals 0. That's the point normal form of an equation of a plane. It's called point normal form because you're given a point and the normal for the plane, And you're using a point and a normal vector to define the plane. So it's a point normal form. You're describing the plane using a point and a normal vector to that plane. Okay, so now okay, so P naught P as a vector that's starting at point P naught and going to point P could be written as x minus x naught comma y minus y naught. And that's if you're talking about a line. That's if you're talking in two, yes, that's if you're talking about in two space, if you start at the point P naught and you're going to point P, right? And P naught P, it's a vector from P naught to P in R2. Okay, and then P naught P is equal to x minus x naught, comma y minus y naught, comma z minus z naught. And this is for a plane, right? So along a line, if you take 2 points on the line, here's your line. Oh, sorry, not R, not, yeah, I guess in R2, yeah. Okay, so we're gonna stay in R2. Okay, so in R2 there's a line, and then you're taking 2 points at line P naught and P, and you're getting this. Now in a plane, here's your plane. So here's your plane, and if you take the point P naught here, and then right when we were talking before, you had the point P naught, and then we traveled to a point P on the plane, and we took a vector from P naught to P, directly from P naught to P. That vector, by the definition of P naught P, is x minus x naught comma y naught, because the points for P naught are, point P naught is x naught comma y naught comma z naught. The point P is x comma y comma z. And so then that means that from P naught to P is x minus x naught, comma y minus y naught, comma z minus z naught. What do you have to add to x naught to get x? X minus x naught. What do you have to add to y naught? What do you have to add to y naught to get y? Y minus y naught. So, okay, so P naught P in a line or plane, there's two, it looks just a little different, okay? And so equation 1 that I wrote on the last board can be written as this. A times x minus x naught plus b times y minus y naught equals 0. And that's for a line. Okay, and here the normal n is a comma b. And then here a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. That's for a plane. And here the normal vector is a comma b comma c. Okay, and these are called component forms. Right. So the other thing was the component forms, because there's just two equations there, so two of them, so it's component forms. In the other example, it was the point normal form, because we used a point and a normal to describe the plane. Here, we're using the components of all the vectors involved in order to describe the plane. Here, we're describing the plane as the set of all points x comma y that satisfy that equation. And what we use for the equation are the components of P naught, x naught, and y naught, and the components of the normal a and b. And so we're using the components of the normal vector and the point to describe the plane, and that's why it's in component form. Okay, here it's just as a plane, and we're in 3 spaces, so now there's just a little bit more, few more components. Here we're describing the plane as the set of all points x comma y comma z, that satisfy this equation, this whole thing equals 0. And what we use to determine that plane are the components x naught comma y naught comma z naught, the components of that same point, and the components of the normal, a, b, and c. So we're using the components of the same two vectors, but we're using its components, not the vectors themselves. And so that's why it's called component form. Okay? And so this is a little bit difficult, but then in an example, it's a little bit easier. Okay? So these are component forms, and you can call them point normal equations of the line and plane. Point. Okay, so we read that. Okay. Okay, so now, okay, so let's do example. So in example 2, in R2, 6 times x minus 3 plus 1 times y plus 7 equals 0 represents a plane with normal vector n, which equals 6 comma 1, and a line. That's example was a plane. Represents a line with normal vector n equals 6 comma 1 through the point. So that this point is on the line through the point 3 comma negative 7. Okay, so y, right? Y, right? Okay, so we said before that n dotted with p naught p is equal to 0 represents a line. Okay, so here what we know that matters is that n is equal to 6 comma 1, and the point p naught goes through the point 3 comma negative 7. And so I'm going to choose p naught to be the point on the line. My point on the line, p naught is any point on the line, and so since it goes through 3 comma negative 7, p 3 comma negative 7, p naught is going to be that. So p naught is going to equal 3 comma negative 7. P is an arbitrary point on the line. P is an arbitrary point on the line. Arbitrary point on the line means it could be any point on the line, including p naught itself. It could be any point. So p is just going to be an arbitrary point on the line, and I'm going to call it x comma y. So the coordinates of a point in 2 space, but in addition to p equal x comma y, we know it's a point as well. So n dotted with p naught p equals 0, that equation translates to taking the vector 6 comma 1, which is the normal, dotting it with p naught p. Well, if p naught is 3 comma negative 7, p is x comma y, then the vector p naught p is equal to the vector x minus 3 comma y plus 7. X minus 3 comma y minus negative 7. And that's equal to x minus 3 comma y plus 7. So the vector p naught p is equal to x minus 3 comma y plus 7. Okay, so p naught p is x minus 3 comma y plus 7. Okay, so n is 6 comma 1 dotted with x minus 3 comma y plus 7, that equals 0. Okay, so I just substitute n for what it is and p naught p for what it is, and the stop part is 0. And so that means that you take the first component 6, multiply with x minus 3, plus this first component of this, times the second component of this, times the second component of that, 1 times y plus 7, and that equals 0. And technically, and so that's the correct way to deduce the equation of the plane from this equation, knowing the normal and p naught, and then saying an arbitrary point is x equals y. Okay, so from this you get that equation. All right, and a simple way to remember it is just that the first component n goes here, the second component of n goes there. Then it's x minus the first component of the point on your whatever you're talking about, line or plane. Y minus the second component, y minus -7 is y plus 7 there. Okay, so you can just match up the components of n or the coefficients here, and then the components of p naught are the things you're subtracting from the x, y, maybe z or w, how many, it depends on how many coordinates you're thinking of, right? In this case, we're talking about an R2, and so we're only going to have x and y, we're only going to have 2 components for each vector, and we're only going to have the sum of 2 things here. In R3, so in R3, if we were to talk about the plane with normal n, which is equal to 4, 2, -5, and it goes through the point 3, 0, 7. So if the plane with that normal and goes to that point, then what you get is that the equation representing it would be the first component is a 4 times x minus 3 plus 2 times y minus 0 plus -5 times z minus 7, and that would equal 0. And you could then write -5 times n sub plus -5. And so this is the equation that would represent the plane with that normal going through that point. Okay, the plane is determined by a normal vector with that plane and a point on that plane. It has to be the set of all points x, y, and z that satisfy that equation. Now you could rewrite this equation a different way, right? So you could multiply these things out, you could add things. So you could write a different equation that's equivalent to it. You could write another equation with the same solutions as this one. But the plane is not this equation. The plane is the set of all points that satisfy that equation, right? And so having an equivalent equation, an equation with the same set of solutions, doesn't contradict the fact that this equation represents a distinct plane. You're just finding another way to describe the same plane, a different equation that gives the same solution, has the same solutions, that describes the same thing. Okay. Okay, so theorem 3.3. So if A and B are constants, not both 0. So then ax plus by plus c equals 0. That's equation 4. So if A and B are constants on both 0, then ax plus by plus c equals 0 represents a line in R2. With normal n equal a comma b. Okay, B, if A, B, C constants, not all 0. So some of them can be 0, but the condition is not that none of them can be 0. It's the condition is that they all can't be 0. So if A and B were 0 and C was 5, that would be fine. So if A, B, and C are constants not all 0, then AX plus BY plus CZ plus D is equal to 0. that's equation 5, and 3.3, represents a plane in R3 with normal n equals a, b, c. Okay? So that's theorem 3.3.1. So in B, theorem 3.31, if a, b, c are constant equals 0, then this equation represents a plane R3 with normal n equals a, b, c. Okay, and so the easy way to remember it is the components of n, a, b, and c correspond with the coefficients of x, y, and z. So the first component of a is the coefficient of x, the second component of n is the coefficient of y, and the third component of n is the coefficient of z. And similarly here, the first component of n is the coefficient of a in that equation, and the second component of n is the coefficient of y in the equation. Right? It's not the letter that matters. If I said n is b comma a, I would have to put a b next to x, right? So it's not the letters that are determining. It's not the letters you choose that are determining this relationship. It's the fact that this is the first component of n, that's the coefficient of x, and the second component of n is the coefficient of y. And similarly, okay? So it's not about the letters. It's about where you put them. Okay. So n dotted with x is equal to 0, and that's equation 6. And this is a really short way of writing all of that. And so we can now succinctly say the things we said, which is n dot x equals 0. And so here n is the vector of coefficients. That's your normal vector. Normal vector. And here x is the vector of unknowns. Is a vector of unknowns. Okay. So what could happen is that you can take the coefficients here to be such that the d doesn't matter. Okay, so in a sense, you want to make your choice of a, b, and c, and x, y, and z, so the d doesn't matter. So we'll do that. Okay. All right. In R2, that equation n dot x equals 0. That's equation 6 from last board. In R2, equation 6 is the vector form of a line through the plane. Through the origin. Okay. Now, okay. This is the form of a line or plane if it goes to the origin. Okay. So in the previous equations, we had ax plus by plus c equals 0, or we had ax plus by plus cz plus d equals 0. So we had a c and d here. And so the n is a and b, and the x is actually representing x and y, x comma y, or x, y, z. And so there's a notation that mathematicians use where x is equal to x comma y, or x is equal to x comma y comma z. And so it's shorthand notation. So we don't mean the same x here as the x here. It's just instead of writing out x comma y, x is representing the ordered n tuple where the first component is that thing there. So the first component, And so it's just having to write less, okay? So x here is really x comma y in the first equation, or x comma y comma z in the second equation. And so n is now still a comma b in the first equation, where n is a comma b comma c in the second equation. But now we're saying it's going through the origin. And so the c and the d here end up being 0. Okay. So that equation is a vector form of a line through the origin. And so it's a way to express a line through the origin. It's called a vector form. Okay. In R3, that equation 6 is the vector form of a plane through the origin. Okay, so in R3, the vectors n and x that you're dot producting and the vector 0, oh no, that's another. The vectors n and x are 3 tuples, and in R2, n and x are 2 tuples. Okay, so this is expressing a line or a plane, depending on the vectors involved. Okay, and so that is the end of that idea. The next thing we want to talk about now is going to be how to decompose U into a sum of 2 orthogonal vectors. The first being a scalar multiple of a given vector A, of some vector A, of vector A, I'll just say, and the second being orthogonal to A. Okay, so how to decompose U into a sum of 2 orthogonal vectors, the first being a scalar multiple of vector A, and the second being orthogonal A. So there's exactly one way to do this. Okay, so there's exactly one way to take a vector U, expresses a sum of 2 orthogonal vectors, the first being a scalar multiple of a vector A, and the second being orthogonal to that vector A. Okay, so this is done exactly one way. It can only be done exactly one way. Okay, so this determines 2 vectors. So decomposing a vector U into sum of 2 vectors in this way, there has to be exactly one choice of those 2 vectors. So let's say you have a vector U here, right? And let's say you have a vector A here. Well, I'm going to call this point Q. Okay, so I'm going to make the vector U and the vector A have the same initial point Q. And so what I want are I'm going to decompose U, expresses a sum of 2 vectors, one which is a scalar multiple of A, one is the orthogonal A. Okay, so now I'm going to choose this vector W1. So geometrically, I'm going to explain to you what's happening here. I'm going to show it geometrically. So the W1 here is if you take the U and you drop a perpendicular to A from the terminal point of U. So if you take the terminal point of U and you drop a perpendicular from the terminal point of U to the vector A, then where the bottom of that segment is, right? Where that touches the point A, if I take a vector W1, it starts at Q and ends at that point. That's going to be the first vector in my decomposition, right? And so the goal is to express U as U equals W1 plus W2, where the other conditions hold, where W1 is a scalar multiple of A and W2 is orthogonal to A. So this is, we're given A here. And then W2 is just going to be the vector that I have to add to W1 to get U. And so W2 is going to be now this vector. And so once I've found W1, finding W2 is really easy because W2 is just the thing you add to W1 to get U. And so U is going to equal W1 plus W2. And so that means that W2 is going to equal U minus W1. And so by geometrically finding W1, I know I already had U with the V from the beginning. I'm subtracting that W1 I found here, and that's going to determine W2. Okay. Okay. And so intuitively, let's see why there's only one possible way to do this. So if you wanted a vector W1 that was somewhere on A, and then I wanted, wherever I ended up on A, I wanted another vector perpendicular to it that would get me to the terminal point of view. Well, if I'm traveling around A, and the only other direction I can go now is perpendicular to A, then think of moving perpendicularly to A. I have to end up at the terminal point of view. And so if I sweep back and forth along a line that's perpendicular to A, there will be exactly one line that's perpendicular to my given A and which will go to the terminal point of view. And so when I sweep back and forth along A with a line that's perpendicular to A, I'll have to stop at a point, but that line then is able to get to the terminal point of view. And there's only one. If I go anywhere else, that line is not going to hit the terminal point of view. Then when I stop at that line, then the point where that line crosses A, that has to be my W1, because I have to then add the vector along that perpendicular line, the right length, to get me to U. And there's no other way to get to the terminal point of view. Okay? Does that make sense? Okay, so here's another little bit. This is probably the first way okay. So here's A, and here's U. And now I want a vector that's a scalar multiple of A, and the same along the line through A is a scalar multiple of vector A, and then add with R. So here I'm going to think of the line through this vector A. Okay, that's the line through the vector A. And so I want to end up somewhere on this line, and then move perpendicularly from that point to get to the terminal point of A. So here's I'm going to draw a perpendicular from the terminal point of U to A. And with the point where I end up, that's where I have to go along that line in order to then move perpendicularly to get to the terminal point of A. And so now this vector is going to be W1, and then that vector is going to be W2. And so now U is equal to W1 plus W2, where W1 is a scalar multiple of my given A, and W2 is orthogonal to A, W1. Well, it's also orthogonal to A, but the same line. Okay? We managed this W2 is orthogonal to A. Okay? Now, saying W2 is orthogonal to W1 is the same as saying orthogonal to A. Okay. And now if you take, let's say you take this U here, and something you might not think of, let's say U is going there, let's say A is going in the complete opposite direction. Okay? It doesn't really matter which A, the line through A, right, is going to go back and forth in either direction. Okay? So regardless of what direction A is going in, the line going through A is just going to go in both directions. So, right? Okay, so here's the line through A. And so I have to end up at I'm drawing a perpendicular from the terminal point of view to that line through A. I'm going to get to this point. And at this point, here's my point Q. Let's call it Q here. I'm going to call it Q here. The vector from Q to that foot, right, of that perpendicular, that's my W1. And then to get to the terminal point of view, I'm going to then go from that point to the terminal point of view, and that's going to be W2. And now U is equal to W1 plus W2. Again, where W1 is a scalar multiple of A, and W2 is orthogonal to W1, or W2 is orthogonal. Okay? And so geometrically, in these three examples, we see how we decomposed U into a sum of two vectors, one that's a scalar multiple of a given vector A, the other that's orthogonal, so that could be the same given vector. Okay, so geometrically, that's how the picture looks for finding that decomposition. Now, next, we're going to more rigorously find the decomposition of a vector A given another vector A. We're going to more rigorously find the decomposition of a vector U given some vector A. Okay? Okay, sorry, I'm actually going to, no, sorry, I'm going to just write the steps for the geometric one. So 1, drop a perpendicular, we'll do that later. Drop a perpendicular. So step 1, what I did was drop a perpendicular from the tip of U to the line through A. Okay, and then step 2, what I did was construct the vector W1. From Q to the foot of the perpendicular. And then 3, the third step was construct the vector W2 equals U minus W1. Okay, so those are the 3 steps from what I just did before geometrically in those 3 examples. Okay, so theorem 3.3.2 is a projection theorem. Okay, so if U and if U and A are vectors in n space, and if A does not equal 0, then U can be expressed as in exactly one way in the form U equals W1 plus W2, where W1 is a scalar multiple of A, and W2 is orthogonal A. So theorem 3.3.2, projection theorem. If U and A are vectors in n space, and if A is not equal 0, then U can be expressed in exactly one way in the form U equals W1 plus W2, where W1 is the scalar multiple of A and W2 is orthogonal to A. Okay, so that's what I was saying before when I was showing the pictures. That's just called a projection theorem. And so that's exactly what we do. Okay. Okay, so so now I'm going to explain how you find W1 and W2 more rigorously. What is the exact vector, what that is, not just the picture. So W1 is the projection of U onto A. Its equation is that's equal to U dotted with A over the norm of A squared times A. This is the vector component of U along A. And now W2 is equal to U minus the projection of U onto A. And that's equal to U minus U dot A over the norm of A squared A. And this is the vector component of U orthogonal to A. Okay, so that's W1 and W2. Okay, so this is equation 10 in this section, and this is equation 11. Okay, so again, with our pictures from before, if this is a vector u, and this is the starting point q, then here's a vector a, right? And so the vector component of u along a, right? The goal, remember, was to write u is equal to w1 plus w2, right? Where w1 is along the line through a, and w2 is perpendicular a. If w1 is a scalar multiple of a, w2 is a orthogonal a. Now, so here, when we draw the perpendicular here, we find w1, and then w2 is the thing you add to it to get u, right? This w1 is the projection of u along a. w1 is this. It's the vector component of u along a, right? The component of u means which one of the two vectors you add to get u. So the components of u are each of the two vectors, w1, w2, that you add to get u. So one component is w1, the other component is w2. And so the vector component of u along a, right, is the vector that's a scalar multiple of a. The vector component of u orthogonal to a is the w2 one, because that's the vector that's orthogonal to a. So w2 here is this, which is the vector component of u orthogonal to a. This is the vector component of u orthogonal to a. This is the vector component of u along a. Okay, and so maybe I'll show you why that is. So, okay, so for w1, this vector, what we want is, let's look at what u dot a over the norm of a squared times a is. Well, u dot a is the norm of u times norm of a times cosine of the angle between u and a over the norm of a squared a. I just replaced u dot a by the definition, norm of u times norm of a cosine theta. Well, the norm of a's cancel in the numerator and denominator. You get the norm of u times cosine theta over the norm of a times a. Okay? Well, the norm of u cosine theta, what that is if you look at this triangle here, you have a triangle here where this is q. This is one side of that triangle, this is the other side, and this is the other side. So by trigonometry, u here, that's the vector u, and so the length of this segment is the norm of u of this triangle. Theta is the angle between, this is not a, but the vector a is in the same direction as this. And so theta is the angle between u and a. This is theta. So there's theta. So the norm of u cosine theta in this triangle is just the cosine theta is defined as the ratio of this side over this side. And so if you take the ratio of this side over this side and multiply it by this length this side, what you get is the length of this side. So the length of that side is the norm of u cosine theta. That's the length of this side of the triangle by trigonometry. Okay? And so now, now what you're doing is you're taking the norm of u cosine theta, the length of this side of the triangle, and all you're doing now is you're multiplying it by the norm of a over the norm of a. So if you multiply this by a over the norm of a, that's the unit vector in the same direction as a. Okay? So the result is you're taking a vector of a unit vector in the same direction as a, and you're multiplying it by the length of this triangle. And so you're taking the length of this triangle, multiplying it by something of unit length, and so you're getting a vector who has length, the length of this triangle here. And then, since it's a over the norm of a, since it's a unit vector in the direction of a, you're taking a vector that has the correct length to be this side of the triangle, and it's in the direction of a. And so w1, if you set this equal to w1, if you set this thing, which is this thing, equal to w1, w1 being equal to this is a vector with this side length that's in the direction of a. And so that is the side of this triangle that you want. that's perpendicular to this that will get you to A. And so W1 should be equal to this, because then W1 is the side of this triangle, the length of this side of the triangle that's in the same direction as A. Okay? And then W2 is just U minus that double W1 we just found. And does U minus that. Okay, and so that's the explanation of those equations. Okay, and so we are now out of time, and so next time we will go over an example of how to calculate W1 and W2 using those equations. So thanks for tuning in to online lesson number 2 for linear algebra, and keep watching the videos. Okay, see you next week.